Hello and welcome to the lesson on building automation system communication. Watch this video to learn how electrical properties like resistance, voltage, and current are used to transmit information on BAS networks. To get started, let's review how a commercial heating, ventilation, and air conditioning system works. To keep occupants comfortable, a commercial building will use a boiler to heat a building in winter and an air conditioning chiller to cool the building in warm weather. Either the boiler or the chiller loop contain a working fluid, which is typically water, that loops into a bulk air handling system. Notice as fresh outdoor air comes in, it ends up mixing with return air that's coming back from classrooms or other rooms in a commercial building. This mixed air is pushed or pulled by a fan across the heating or cooling coils, depending on the season, and that air then travels its way to the room or zone that it's conditioning. Each room may need a little bit of temperature tuning depending on if the room gets too hot or too cold. And temperature tuning at the room or zone level can be done by a variable air volume box. Let's talk about that variable air volume box on the next slide. Here's an image of a variable air volume box, or VAV box. This is used to tune the temperature in a room or zone of a building. A VAV box may have both the heating and cooling coil in it, but this one just has a heating coil. I can tell that because I can see some hydronic piping that likely supplies boiler hot water to the coil. And once the air blows across this coil, the return boiler water goes back to the boiler to be reheated. So if there's only a heating coil, that means all of the cooling during the warm summer months is provided by the bulk air handling system. And that cool air is brought into the room with the fan, and the heating coil stays shut during the warm months. In order to temperature tune the room, if it's calling for heating, a damper will first open to let in that mixed bulk air, and a variable air volume fan will start. Next, a valve actuator opens to let hot water from the boiler into the heating coil. Mixed air from the bulk air handling system will flow across the coil to heat the room. Let's think about that room as we move to the next slide. Consider that room is uncomfortably cool. What building automation system components would be used to provide heat to the room? As you may recall, the building automation system components that help to control the temperature in the room include a temperature sensor, which indicates the temperature of the room. The temperature sensor in this case reports its 66° Fahrenheit temperature. Where does that temperature message go to? The 66° Fahrenheit reading from the sensor is reported to the controller. As this slide reads, the controller is a digital processing system that collects data from sensors, monitors the data, and sends out digital commands. You heard an emphasis on the word digital, and that's because we'll be focusing on digital communications as part of this lesson. The temperature sensor is an input to the controller. But what does the controller do from here once it receives a temperature reading of 66° Fahrenheit, which is below its set point? The controller is programmed to respond to the input it receives. The program stored on the controller is created using a PC or other type of workstation interface. Oftentimes, this programming, a type of coding, is done using block logic in building automation systems. We won't spend a lot of time on block logic coding in this introductory class. More advanced building controls and information technology classes teach you how to code automation control logic. While the building operator's workstation screen may show a graphic and temperature set point, the logic saved to the controller is often not visible to the operator. The operator may view a 66-degree temperature on the workstation that is being received from the sensor in a room. And then the logic saved to the controller commands what happens when the temperature sensor reports a temperature that is being sensed below set point. The logic program saved in the controller directs a valve actuator to open, allowing heated water to enter the heating coil. The heating coil warms up. The fan will start and draw in tempered mixed bulk air across the heating coil so that it may enter the room, warming the room to the desired temperature set point. To recap, you just saw how the temperature sensor reports to the logic controller, which is programmed with logic that commands the valve actuator to open and also the fan to engage, which draws in the mixed bulk air across the heating coil to warm the room. It is important to understand how these BAS components, sensor, controller, and actuator, are connected. The connections allow the BAS components to communicate. It is important to understand how these BAS components, sensor, controller, and actuator, are connected. The connections allow the BAS components to communicate. Communication between sensors, controllers, and actuators is typically done digitally. Let's define this word digital. Digital is defined as the use of signals or data expressed as a series of digits, zeros and ones, which are typically represented by values of a physical quantity, such as voltage or magnetic polarization. BAS systems use digital messages communicated as electrical voltage, electrical resistance, measured in ohms, and also electrical current, measured in amperage, to communicate across BAS networks. For example, the building automation trainer that you'll use in this class uses a thermistor-type temperature sensor that communicates temperature as electrical resistance measured in ohms to provide a temperature reading. Thermistor-type temperature sensors are made of a semiconductor material that changes its electrical resistance as the temperature changes. This graph shows the relationship of electrical resistance to temperature for the thermistors used in this class. As the temperature increases, the resistance goes down. To show the electrical property of resistance changing with a wall plate type thermistor. Here, a student's connected a digital multimeter, making sure the leads are in the correct place to measure ohms. We can see the units are ready to measure kiloohms. And we can also see how the resistance changes as the temperature of the wall plate thermistor changes. Let's see what happens. As the student warms up the thermistor plate with his hand, the resistance goes down just like we saw in the temperature resistance chart on the last slide. Temperature readings are common network points in a building automation communication system. As you learned, temperature points may be measured using a thermistor-type sensor, communicating temperature as electrical resistance measured in ohms. Ohms, or other digital representations of temperatures, are reported as digital messages programmed into a digital code within a BAS network. The digital message is received as an input to the BAS controller. Imagine that each point in the building automation communication system has its own address, and it sends messages through a coding system. We illustrate this idea by showing the code delivered just like an envelope in the US mail. In real life, the digital codes can be sent on a BAS network using wires, Wi-Fi signals, Bluetooth, or other digital forms of communication. Let's see how this message code travels through the BAS network. What we may see as a temperature reading, the controller may read as electrical resistance measured in ohms. Recall that the controller contains logic, which tells the system what to do when it receives a certain measurement as an input that may be below the room's desired temperature set point. The logic code will issue an output from the controller as a digital message. The logic code will issue an output from the controller as a digital message. In this case, we can see the digital message will turn on the heating coil and fan to on. This output message is oftentimes communicated in volts of electricity, which we'll talk about in a few minutes. On-off signals can be sent as voltage through a relay that opens or closes the electrical connection. When the relay opens an electrical contact, the voltage is not transferred through the contacts. When a relay is closing the contacts, voltage transfers through, completing the electrical circuit. Let's take a look at how the controller works on the trainer using voltage to control the fan. Here we can see that we have a digital multimeter that measures voltage as well as a variety of other electronic properties. And the switch has been turned to measure voltage in this case. If you take a close look at the digital multimeter, it can measure alternating current represented by the wavy voltage line, also called AC current. The meter also is capable of measuring DC or direct current, represented by the yellow straight and dashed lines. Notice that AC is the default display. The fan and light on the trainer run on DC, so you will want to make sure that you push the yellow select button to switch the digital multimeter reading to DC. You will have the opportunity to measure voltage output signals as part of your BAS training activities in this class. The next several slides provide an overview of how to measure relay voltage control outputs from the controller to the fan. The name brand of the controller on the trainers is called Contemporary Controls. This company provides a wiring diagram to help us understand how binary outputs use voltage to control the fan. This diagram shows you that your fan could be wired to any pair of these relay terminals. On our trainer, the relay for the fan is marked as binary output 2, or BO2. On the trainer, the outputs face the top of the trainer. The wiring diagram shows that the black wire connects to the negative terminal of the power source directly to the fan. The red wire comes from the positive terminal of the power source and through what's called a relay in the controller. A relay is an electromechanical switch that opens or closes an electrical circuit. If we measure voltage between the negative black terminal and the second terminal of the relay circuit, we should be able to measure a 24-volt signal because that's representing a closed circuit. Voltage will conduct through that circuit and the fan will turn to on. If the relay is open, we would measure a near zero voltage and the fan or other powered device would be turned to off. As part of your lesson, you will explore how to measure the communication signals to and from the relay output on the controller. To do this, you will see if the circuit to the fan is either open or closed. And to open or close the circuit, the controller will open or close a relay that opens or closes the electrical connection between terminals 3 and 4, the binary output 2 on the controller. So binary output 2 controls the fan. So if this circuit is open, the electrical signal will not pass through and the fan will remain off, which if you are listening, you can't hear the fan running, so it sounds like that should be the case when we try to measure this. And when it is closed, we will measure the same voltage between these two terminals, indicating that the circuit is closed and the fan is running. So we can do this measurement of the fan relay by making sure our digital multimeter is set to measure volts in DC. So we can see it's on DC voltage, and we will begin by putting the negative probe into the negative 24 volts DC part of the terminal strip. So we can see that just stays there. And then we'll measure on the binary output side of the controller at terminal 4. And the digital multimeter is reading 27.68 volts DC. So that indicates there is 24 volts of power supply, even a little bit more is finding its way to that terminal than 24 volts. And if we measure the other side of that relay, remember we're expecting it to be open, and it looks like it is. The relay is open, the circuit is open because we're receiving negative 2.3 or so volts through measuring that part of the circuit. So again, we had at terminal 4, power supplied at 27.68 volts or so. And then at terminal 3, we are measuring -2. So it looks to me like the voltage between those two is very different, not near 24 volts, which is the power that this fan uses. You can read there's 24 volts required to power the fan. So obviously when we're measuring -2 at terminal 3, that would mean that the fan is not receiving the full voltage that it needs to run. So let's engage the fan. And we're going to do that by doing something you would never do in real life, because the object is to save energy here. And this room is already sensing that it's above 72.4 degrees. No need to really turn on a heating coil, but just so we can get the fan to run, and this is in unoccupied mode, we're going to turn the unoccupied temperature set point above the room temperature, 72.3. So I'll turn it up, it looks like, to 75.5. And again, we would never do this in real life, but we just want the fan and light to engage. So now we can see that has turned on, and we'll see if we can measure more than 24 volts across that relay terminal. And this whole time we have left the negative digital multimeter probe in the negative part of the terminal strip. And now if we grab the other side of the digital multimeter, the red probe, and we measure at terminal 3, we'll be able to see that, yes indeed, this is measuring now the 26.7 volts, which is the same voltage, or near the same voltage that we measured at terminal 4. So that indicates that that relay was controlled by the temperature set point. We increase the temperature set point, which has been programmed into the controller to turn on the fan and the heating coil, which is represented by the light. And it will continue to run until the temperature set point is met. we have a controller that I have not wired, so I can discuss a fundamental, important concept to know about automation signals. And that is, BAS communication signals are divided into two categories, binary or analog. The fan and light used in the building automation trainer is either on or running, or off, not running. Devices or signals that are either on or off are called binary. The light is wired to binary output 1, and the fan is wired to binary output 2. The thermistor, temperature input, provides a continuous input of ohms and is wired to what is labeled UI1 over here. You may wonder why the temperature input terminals are labeled UI. That is because BAS controllers like this one may allow the user to configure the input or the output to be either binary or analog. The type of terminal that can be programmed as either binary or analog is called a universal input or output. Overall, you will notice that we do not use the full input and output potential of this controller. And one more thing, did you notice that the inputs and outputs come in pairs of terminals? That is because an electrical signal flows through one terminal and out the other. The voltage measurement through the relay is a good example of why there are two terminals per output. In summary, digital communication involves sending electrical signals as messages. The controller is programmed to respond to those digital messages, and messages are either binary, on, off, or analog, which represents a continuous range. You are off to a smart start in learning about building automation systems with this lesson. What you just learned are skills that are in very high demand. Learn how to do this job well, and you can enjoy a future in building automation system technology.